All right, math, advanced math 8. Almost called you guys math 2, but no, you're not that. So anyways, we got lesson 5.2.2. This is arithmetic sequences. And we saw in the last lesson that arithmetic sequences is when we were adding or subtracting a number to get to the next term. Now, with sequences, they're different than all the other stuff that we've been graphing before, because with the sequence just has each term written down with no x and y. There's just the number written down as a list. And sequences have their own way to write things, so their own notation, and then their own vocabulary that goes along with them. So we've already talked about a term and a term number. These are our terms. And then the term number, remember, was where we said, okay, this is the first term, this is the second term, this is the third term. So up here, this is the term number, which is the part that's not written for in a sequence. And then down here, these are the terms. And the terms are the only things that are written in a sequence. All right, so looking at this first one that we have here, we want to see what kind of pattern is developing here. So are we adding or subtracting each time? That would make it arithmetic. Are we multiplying or dividing each time? That would make it geometric. Or is it neither one of those? And there were neither. Remember, we had Fibonacci, that sequence, that goofy one where you're adding the previous term, two terms each time. We weren't adding the same number, so that didn't make it arithmetic. And then we had the ones with squares. Squares were not geometric because you weren't multiplying the same time. You were squaring numbers. So there are things that are neither. Okay, so it's not either arithmetic or geometric. There's other things out there. So arithmetic would be we're adding and subtracting, and of course we are adding and subtracting. Here's how we can tell. We can tell that we are adding 4 each time here. So I add 4 and get -1. I add 4 and get 3. And I add 4 and get 7. So, 4. So I can see that the constant number that I'm adding each time is 4. So that makes it arithmetic. We are adding the constant value. So that means it's not changing. It's always going to be 4. The constant value of 4 each time. What's the first term of the sequence? -9 is. Now we call the first term of the sequence t of 1. So that's the first term in the sequence. The common difference is the constant number added or subtracted to each term. So the common difference in this case is 4. So the common difference is 4. A lot of times we give this a D. So for common difference, so the common difference would be 4 each time. Okay, record the sequence in a table. The sequence compares the term number, n, so this is going to be our term number, with the term value, or the actual term. So remember, the terms are what they give us. They gave us -9, -5, -1, 3, and 7, and we could find the next term because we were adding 4 each time. So the next term would be 11 for this one. The term numbers, we always start with the first term. The first term is -9. The second term is -5. Third term, fourth term, fifth, and sixth. So these are the term numbers. These are the parts that aren't actually given to us in the sequence. We're just assigning the term number to the order that we see them in the actual sequence. Okay, now we're going to graph the sequence. So for this sequence, we know that we're never going to have a term number that is going to be negative. We can't have a negative term because we only started the first term. Okay, so I can, with some confidence here, say that, okay, I'm going to make sure the x-axis, we're just looking at the positive side of the x-axis. All right, so where am I going to put it? Right here? Oh, wait, I need negative numbers. Ah, ha, ha, ha. So 1, 2, 3, 4, 5, 6, 7, 8, 9. That's good enough. All right, so we'll put it right here. So this is going to be the term number. That's going to be our x. And then our actual terms, which are what the sequence are on, is going to be over there. Okay, so term number 1 is -9. So term number 1 is 1, 2, 3, 4, 5, 6, 7, 8, 9. There's my first term, -9. Second term is -5. 1, 2, 3, 4, 5. Third term, so term number is 3. Third term is -1. Fourth term is 3. Fifth term is 7. And then the sixth term is 11. Oops, I didn't go up high enough, did I? There's 7. The next one's going to be 11. 1, 2, 3, 4. There you go. Not bad. You're not a term. All right, so there's all of my terms there. And we're seeing that with arithmetic sequences, we are getting, right there, a nice line. So how is the common difference related to the graph? Well, the common difference, it looks like it's the slope. So the common difference is going up 4 and over 1. So if I do a slope triangle between these, I'm increasing by 4 as the term number goes up by 1. So the term's value increases by 4 every time the term number increases by 1. So the common difference is the slope of the graph. Okay, we want to write an equation to model this. Now, this is where it kind of breaks down a little bit because we have a first term, we don't have a 0 term, but we usually need a y-intercept in order to graph something. So I already know that my terms are going to be t of n, and n is my term number. So this is like my y value, and this is my x value. So to write an equation here, I'm going to say t of n, that's my y value, so these are all my terms, is equal to, now we're increasing by 4 each time, so that's our slope. And then our x value is the term number, and we called that n. Now we just have to see where that would start on our graph, and it doesn't start at -9. Because remember, where we cross the y-intercept, that is where x is 0. There's technically not a 0 term. But we could just subtract 4 from this term right here, because if we were adding 4 this direction, we could subtract 4 going the other direction. So if I subtract 4 from -9, I get -13 here. And there's my equation for my sequence. So the term is equal to 4 times the term number minus 13. And then if I plugged in 6th term, 4 times 6 is 24, and 24 minus 13 is 11. So the sixth term is 11. Okay, what is the domain of the sequence? Well, our domain cannot be 0. And also, my domain can't be fractions. So this is going to be a little bit different than what we've seen before. We're going to say that our domain is the set of the positive integers. Now, what's an integer? Positive and negative whole numbers. But I can't have negative term numbers. My terms start at 1. So I'm going to say it's only the positive integers. 0 is not positive. So we're going to say that it's the positive integers. Those are my possible term numbers because our domain is our term numbers. And I'm starting at 1 and then increasing by 1 each time up there. Those are integers, and they're only the positive integers. What is T of n if n equals 0? Well, T of n if n equals 0, when n equals 0, that's the y-intercept. That's negative 13. What value is this in the equation? That's our y-intercept. All right, the initial value, which is usually what we've called our y-intercept, we're going to call the 0th term, and we're only going to be using this for the equation. It does not exist in the sequence. So in our sequence, up here, I never saw negative 13 in my sequence because the 0 term doesn't exist. But we need the 0 term to write the y-intercept here. So we're going to just start saying that the 0th term is the term that doesn't exist, but it's going to be used for our y-intercept. So this is never part of the actual sequence. T of 1, the first term, is actually the first term. So this is T of 1, negative 9. That's the actual first term. There never is an actual T of 0, the 0th term. Okay, so T of n is called the nth term in the sequence. So if I want to find the nth term in the sequence, I use this equation. If I want to find the 7th term, I'm not doing the nth term anymore. I'm going to plug in 7 here, and that'll find the 7th term for me. All right, so let's consider the sequence negative 4, 1, 2, and 5. What's the 0th term of the sequence? Well, I need to find the common difference first. So what's happening each time? Well, it looks like I am adding 3 to get from here to here, adding 3 to get to here, and adding 3 right here. So it looks like my common difference is 3. So that's kind of like my slope. So the 0th term, remember, doesn't exist here. This is not the 0th term. This is the first term. So to get the 0th term, instead of adding 3 this direction, I would subtract 3 going this direction. So to find the 0th term, I take negative 4 and then apply the common difference to it, which would be to subtract 3. So I'm going backwards on the common difference because I'm adding 3 this direction, subtracting 3 the next direction. So negative 7 would be the 0th term. Remember, it's not actually part of the sequence. What's the first term? Well, we call that T of 1, and the first term is negative 4. So this 0th term is T of 0, and that's negative 7. Remember, that's our y-intercept in our graph. What's the common difference? The common difference is positive 3. So you can see here the difference between T of 1, the first term, and the 0th term is us subtracting the common difference to go backwards to find that one. All right, one more page and we're done. All right, write the equation for T of n. Well, so if I want my nth term, I would say that T of n is equal to my common difference of 3 times the term number, n, and then plus the 0th term. The 0th term is -7, so plus -7 would be -7. So that would find all of the other terms in the sequence. Is it possible for any number in the sequence, that's what T of n means, the nth term, to be equal to 42? Well, let's plug it into our equation. So we would say 42, so that's T of n, equals 3n minus 7. I would add 7 to both sides, and I would get 49 equals 3n. Now, if I take 49 and divide by 3, I get 16.33333. So I get 16.3 repeating. So is it possible for us to have a term number, any term number, that's equal to 42? No, because our term numbers have to be positive integers. I can't have the 16.3 repeating term. There is no 16.3 repeating term. So we'd have to say on this one, no. Because term numbers must be positive integers. And 16.3 repeating is not a positive integer. So this is where it's going to be a lot different from equations that we've done with before, or functions that we've done before, because in all of those, they were continuous, which meant that we could have decimal answers and fraction answers. They didn't have to be integers. Whereas for sequences, the term number has to be a positive integer. All right, if this were an equation, could f of x be equal to 42? Yes. And we just said why? Because equations or functions can be any value. Meaning it doesn't have to be integers, so we're talking about fractions and decimals. So that's a big difference between this arithmetic sequence and a linear function. Is the arithmetic sequence needs to be discrete. It can't be connected like we were doing for our functions. All right, 5-59. Trixie wants to create an especially tricky arithmetic sequence. She wants the 5th term to be 11 and the 50th term to be 371. Find the common difference and the initial value of the sequence. All right, so her 5th term, that's an x value. She wants it to be 11. Her 50th term, she wants to be 371. We basically want a function here that we can use. So we want to say, okay, her equation for her sequence, so to find any nth term, we want the initial value of the sequence. The initial value is the 0th term. So that's the y-intercept. And then the common difference, which would be the slope. Well, we can find our slope because we have 2 points here. 5th term's 11, 50th term's 371. So I can do 371. Let's do a different color. So I can say that the common difference is going to be 371 minus 11. over 50 minus 5. And so up here, we end up with 360 divided by 45. I think 45 does go into 360. It goes in there 8 times. So our common difference is 8. All right, so the nth term of the sequence is equal to 8 times the term number, but I still need the 0th term because that's my y-intercept. So in order to find the y-intercept, remember we can do the whole thing where we do y equals mx plus b. Let's just use this point right here. So we plug 11 in here. M is 8. X is 5 plus b. So I got 11 equals 40 plus b. I would subtract 40 from both sides, and I'd get b equals negative 29. So the 0th term would be negative 29. So would negative 29 actually be in the sequence? No. The first term in the sequence would be t of 1, where we plug in 1 here, and that'd be 8 minus 29, which is negative 21. So the first term in the sequence in this case is negative 21. Then the next term, we'd add 8 again, and we'd get negative 13. Add 8 again, the next term in the sequence would be negative 5. And then 3, ... That would be how the sequence would go. This number is not the first term in the sequence. It's the 0th term that doesn't exist in the sequence. All right, Trixie, who seems to be aptly named, wants an arithmetic sequence with a common difference of negative 17. All right, negative 17, and a 16th term of 93. So she wants our common difference to be negative 17, and she wants the 16th term to be 93. All right, write the equation for her sequence. So that's t of n equals, well, I know that I want it to have a negative 17n. All I need is the 0th term. So I'm going to use this right here again, y equals mx plus b. So y equals mx plus b. Instead of y, we plug in 93. Instead of m, we plug in negative 17. Instead of x, we plug in 16 plus b. Negative 17 times 16. So 17 times 16 ends up being, nope, 17 times 16. How to do it a log? I don't know. 272. So this is 93 equals negative 272. And then I'll add 272 to both sides, and I get 365. So my 0th term is 365. So is that the first term in the sequence? No. The first term would be 365 minus 17, and then that would be the first term in the sequence. All right, we're almost there. 2 more problems. All right, your favorite radio station is having a contest. The DJ poses a question, and the first caller to answer correctly wins the prize money. If a caller answers incorrectly, $20 is added to the prize. Sweet. All right, so 14 people have already called in today with incorrect answers. So when you called in with the right answer, you won $735. How much was the prize worth at the beginning of the day? All right, so if you've got 14 people calling in before you, and $20 got added each time, 20 must be our common difference. So the common difference is 20. Now in the sequence, you are the 15th caller. So the 15th caller is the term number, and it's $735. So we just need to find out how much it was worth at the beginning of the day. And that would be T of 0, right? Because caller 1 added $20, caller 2 added $20, and so on and so forth. So if we need to find T of 0, that's the y-intercept. So all I need to do for this one is do y equals mx plus b, and plug in all the numbers that I need to solve that out with. So 15 is my x, 735 is my y, 20 is my m, and then we can solve from there. Oh, wait, I just thought of something. This should be 15. This should be 14. Why? Because 14 was only added, $20 was added 14 times. Okay, sorry, got mixed up on that one. All right, so y is 735, m is 20, our x value is going to be 14, and then plus b. So on this one, I'd do 20 times 14, which would be 280. And then we'd take out our calculator and do 735 minus 280. Comes out to $455. So there's T of 0. Because by the time it got to us, they added 14 people called beforehand. So there are 14 people that were adding $20 because they all got it wrong. So they added $20 each time for that one. All right, got it? All right, next part. On this one, we're going to suppose that the contest always starts with $100. Okay, so that's before we start adding all this. So this is actually T of 0. Because we don't add $100, we're just starting at $100, and then we're going to start adding it. And so when the first caller gets it wrong, we're up to $120. Second caller gets it wrong, we're up to $140. So the sequence would start at 120, then 140, then 160, and so on and so forth from there. Okay, so we want to find out how many people would have to guess incorrectly, and that is this value up here. That's our n value. So we want the nth term to be 1,360. So if I use my formula of T of n equals my slope number is 20, my common difference, times n, and then we know that we're starting at $100, that's T of 0. Now all we have to do is, since we know T of n equals 1360, I can plug 1360 in right here. So I can subtract 100 and get 1260. And then divide by 20. And I should get 63. So there'd be 63 callers in this instance. All right, last part. Write an equation for each arithmetic sequence. Okay, so all you have to do to find a sequence is start by finding the common difference. So all you have to do is pick any 2 points here. So these are our x values, these are our y values. So our common difference is our slope number. So from here to here, I am subtracting how many? 44. And from here to here, I'm subtracting 4. So my change in my y values is negative 44. The change in my x values is negative 4. And I get positive 11. So the common difference is 11. And then all we have to do is y equals mx plus b. So we can pick any numbers here. So I'm going to pick the small numbers. So 10 equals common difference of 11 times 3 for the x plus b. So we get 10 equals 33 plus b. Subtract 33, we get negative 23. So the nth term, or t of n, is equal to the common difference, 11, times the term number, n, and then the 0th term is our y-intercept here, negative 23. All right, for the next one, it looks like we are adding 90 over here, and over here, we're subtracting 30. So our common difference would be 90 over negative 30, which is negative 3. So the numbers are decreasing. Okay, so I can use any 2 points. I'll just use the first 2 points. So y equals mx plus b, so 10 equals negative 3, my common difference, times my term number of 100, plus b. So we got 10 equals negative 300 plus b. I'm going to add 300 to both sides. Just a second. All right, so we're going to add 300 to both sides. We get 310 equals b. So the nth term is equal to the common difference of negative 3 times the term number, n, plus 310. And that is it. The end. All right, math hard, guys. I will see you some other time. Have a great day.